Section 8.4, Part 3. This is example 6. So an automobile manufacturer uses 6 industrial robots that are used as welders on the assembly line. On a given working day, the probability that the robot will be inoperative is 0.05. What's the probability that on a given day, exactly 2 robots are inoperative? So in this problem, because of the way they're wording it, our probability of success is really the fact that the robot's not going to work. So our success in this case is the robot not working. So it's a little bit of a twist on the wording. And we know that we have 6 of them all together. So there are 6 on the assembly line. So part A says, what's the probability that on a given day, exactly 2 robots are inoperative? So that would be the combination of 6, choose 2, times that probability that it's not going to work, raised to the second power. So 0.05 to the second power. And then we need the complement. So 1 minus the 0.05 gives us 0.95. And the difference between the 6 and the 2 is 4. So the probability that 2 of those robots are inoperative, exactly 2, on a given day comes out to be 0.0305. Part B on that problem asks us less than 2 are inoperative. So less than 2. What does that mean? What does less than 2 mean? Well, we're going to translate that to mean that 0 or 1 are inoperative. And that's telling me that what I need to do is figure out the 0, figure out the 1, and then add those 2 together. So we have to work 2 of them and then sum them together. So we'll do the combination of the 6, none are inoperative, so 0, times 0.05 to the 0 power times that 0.95 to the 6th power. And that comes out to be, wow, I don't have that individually. Hang on. Okay, well, 6 choose 0 is 1. 0.05 to the 0 power is 1. So it's really just 0.95 to the 6th power. So, which comes out to be 0.735. Okay, now we're going to come in and do the 0. So, or I'm sorry, the 1 being inoperative. So the combination of 6 choose 1 times 0.05 to the 1st power times 0.95 to the 5th power. So 6 choose 1, 0.05 to the 1st power times 0.95 to the 5th power. So that's 6 times 0.05 and 0.95 to the 5th, which comes out to be 0.232. Then we're going to sum those 2 together. So 0.232 plus 0.735 comes out to be 0.967. So the probability that less than 2 are not working on any given day is 0.967, which is what you really want, right? Because either 0 or 1 not working, that's pretty high. Okay, and then the last part says more than 4 are inoperative. More than 4, that's not good for your assembly line. So again, let's interpret that more than 4. What are they asking us to find? So, I'm sorry, more than 4. Well, more than 4 means what? 4, more than 4 does not include 4. So that would mean either 5 or 6 are inoperative. And again, you can do this number of ways. We've already done the 0, we've already done the 1, we've already done the 2, but we still have to do the 3 and the 4. So I'd still have to do 2 of them. So no matter how I slice it, I need to figure out 2 of them. So we'll come in and do the combination of the 6, 5 are not working, times 0.05 to the 5th power, and then 0.95 to the 1st power. And then we'll come in and do 6 choose 6. That's all 6 of them not working. Your assembly line has been shut down for the day. 0.05 to the 6th power times 0.95 to the 0 power. Okay, let's figure out what each one of those are. This one will take me a little longer because I don't know what the combination of 6 choose 5 is. And hopefully you're doing it right there with me. So, okay, slow down because I'm making silly mistakes. 0.05 to the 5th times 0.95. 6 times. Double checking it, and I get It gives me a scientific notation, so we'll translate it. So 0.000000178. It says 1.78 times 10 to the negative 6. So that means the decimal has been moved over 6 places. So here's 1, 2, 3, 4, 5, 6 places. So it's going to be other one. So 6 choose 6 is 1. So that one's a lot easier to do. So 1 times 0.05 to the 6th power. That one comes out to be 0.000000. Like I count 1, 2, 3, 4, 5, 6, 7, and then 1, 5, 6. So pretty tiny numbers. And to that, I'm going to add the previous answers. So 0.1, 2, 3, 4, 5, 1, 7, 8. And we get as our sum 1, 2, 3, 4, 5, 1, 7, 9, 5, 6. So this 1 is getting added to this 8 is what's happening. So pretty tiny, which is good because that means your assembly line is going to be working, not closed down for the day. So be really careful with the less thans and the more thans. Make sure you write out what it means first so then you can identify what you need to calculate. Okay. Our next example, example 7. Example says the probability that an airplane engine will fail in a transatlantic flight is 0.001. Good thing it's tiny, huh? So in this case, again, our success is actually the engine failing. Assuming that the engine failures are independent of each other, what's the probability that on certain transcontinental flight, a 4-engine plane will experience no more than 2 engine failures? Okay, so we've got 4 engines and we want no more than 2. So no more than 2 means none are going to fail, 1 are going to fail, or 2 are going to fail. So this time we are going to include the 2. So we do each one of these individually. And in each case, X is going to be the 0, the 1, or the 2. So this would be the combination of the 4, none are going to fail. So 4 choose 0 times 0.001 raised to the 0 power times 0.999 raised to the 4th power. Then we'll do the combination of 4 choose 1, 0.001 now to the 1st power. Its complement 0.999 to the 3rd power. And then finally the combination of 4 choose 2, 0.001 now to the 2nd power. And the 0.999 to the 2nd power. Then when you're going to do each one of those individually, and then you're going to sum them all together. And when you're all done, believe it or not, this comes out to be 0.999, and there's a whole bunch of 9s. And then finally, that last digit sitting out there is a 6, but it's really 0.999. So in other words, no more than 2 failing is 99.9% of the time, which is nice to hear if you ever take a transatlantic flight. Okay, the last example actually springboards off of what we were talking about in the previous sections with the average, the mean, the standard deviation, and so forth. So if you have a binomial experiment, then it just happens to be that the mean is found by taking, so the mean, which is again the expected value, is found by taking simply the number of trials times the probability of success. So n is the number of trials, p is the probability of success, and that's the mean. You can find the variance in that random variable by taking n times p times q. So you simply take the expected value and multiply it by one more quantity, which is the probability of failure. And then we know that the standard deviation in terms of x is going to be the square root of the variance. So n, p, q. So the last example, which is example 8, says PAR Bearings manufactures ball bearings packaged in lots of 100. The company's quality control department has determined that 2% of the ball bearings manufactured do not meet the specifications imposed by a buyer. Find the average number of ball bearings that fail to meet. Find the standard deviation that also fail to meet the buyer's specifications. Okay, so let's figure out what's going on. So n is the number in the package, which is 100. P is going to be, in this case, the probability that it does not meet their qualifications, and that's the 0.02. That came from the 2%. So we know that Q then is going to be 0.98. So the mean, mu, which is our expected value, is simply n times p. So it's going to be the 100 multiplied by the 0.02, which simply means that in that lot of 100, there are going to be 2 of them that do not meet the buyer's specifications. That's it, just 2. On average, every lot of 100 has 2 that are not going to meet the buyer's specifications. The standard deviation then is going to be the square root of n, which is 100, times p, which is 0.02, times q, which is 0.98. So again, do the multiplication first and then treat that square root as a grouping symbol. And if you do that, you should get 1.4. So, and that describes the spread of the data. And what we're going to see in our next section, section 8.5, is where standard deviation finally comes back into play. And we'll give it some meaning when we start talking about the normal distribution.